My name is Tushondra Thomas. I am an informaticist with City of Hope. My colleague Nasim Eftekhari, she is a clinical data scientist, and today we are going to talk to you all about our journey towards creating a machine learning algorithm to predict sepsis in bone marrow transplant patients. We have no real or apparent conflicts of interest to report. And by the end of this session here, we hope that you will be able to do a few things. Those include explaining how evidence-based practice impacts technology design, how to apply a nursing evidence-based practice model to an informatics project, describe how to perform an evidence synthesis, define artificial intelligence and machine learning, as well as describe how machine learning can help with clinical decision support. The last objective is explain how methodology and design of a machine learning sepsis prediction model. So a little bit about City of Hope. City of Hope is a biomedical research institution that was founded in 1913. We received Comprehensive Cancer Center designation from the National Cancer Institute in 1998, licensed at 217 beds. And one thing that's really cool, we have 40 cottages on our campus. And this is where family members can stay while their loved ones are receiving treatment. In addition to our main campus, we have 15 community sites. We have seen last year over 6,700 patients on the inpatient side, and just total visits over 212,000. We have a number of medical staff and nurses within our organization that take care of our patients. And from a cancer volume perspective, we are number 4 in California and number 2 in the primary service area. We do a lot of clinical trials at City of Hope. So at any given time, there can be over 500 trials going on with more than 6,200 patients that are enrolled. And as far as bone marrow transplants, so saying hematopoietic stem cell transplants is a tongue twister for me. So I will start to call these transplant patients moving forward. We've done over 14,000 transplants. For those who didn't know, synthetic insulin was created by physicians at City of Hope. And we've also made a number of top-selling cancer medications. So in regards to our survival statistics, post-transplant survival statistics, we have one of the best survival rates, and we're the only organization that has performed above those predictions for survival statistics for 13 consecutive years. So now that you know a little bit about where I work, I'd like to talk about how evidence-based practice can be incorporated into a technology project. So when you think about nurses and informatics, we're used to nurses doing workflow and training and all of those things that are kind of like the nuts and bolts of technology still, but our role is evolving, and I'm very happy to be part of this type of transition. So evidence-based practice, what is it? What does that even mean? So evidence-based practice is basically a problem-solving approach to decision-making. It's where you're using your clinical expertise and combining it with the best evidence available to improve both outcomes as well as processes. There are a number of nursing evidence-based practice models that organizations can choose from, and I won't ask any of you to tell me which ones your organization has, but if you are a nurse within an organization or you support a nurse within an organization, do you know what that evidence-based practice model is? And how often do you apply the steps of that model to the projects that you are working on? So at City of Hope, we use the Iowa model. And I'm just going to talk briefly about how these steps can be incorporated into a project such as what we're working on right now. When you identify issues and opportunities, this is where you go out and you speak to your clinicians. You talk to them and ask them what their pain points are. So it's no different than what we already do. One thing that I can say, when it comes to these transplant patients, identifying sepsis can be very complex. And that's because their presentation is very unique. Post-transplant complications such as neutropenic fever mimic the signs and symptoms of sepsis, so it makes diagnosis a little more difficult in this population. From a nursing perspective, when you state the question, we call that PICO. So PICO defines the problem as it relates to the population, interventions, the comparisons and outcomes. So for our project, we want to know, can a machine learning algorithm predict or detect sepsis risk in adult hematopoietic stem cell transplant patients? When you form your team, you want to identify who has the right expertise to work on a particular project. So again, nothing different than you already know. I'm a nurse by background. Nasim is a data scientist. We have 2 physician investigators, and we've also recently added a clinical data pharmacist, clinical informatics pharmacist on our team. When you look at the design and pilot, again, things that you already know how to do. One thing that you want to also include here is defining or identifying, do you need institutional review board approval for your project? In addition to that, you want to also think about FDA approval. So for those of you who are not aware, machine learning, it needs to have FDA approval at sometimes, depending on what you're actually going to do with it. System integration, is this going to impact one department? Is it going to be multiple departments or a rollout across the entire organization? And when you disseminate your results, of course you do that internally, but externally sharing information like what we're doing today is also very important. So what are our issues and opportunities? Transplant patients are 5 times more likely to develop sepsis than non-transplant patients. And the occurrence of sepsis during their neutropenic phase is anywhere from 70 to 100%. The cohort of patients we're looking at right now includes 676 patients, and of those patients, approximately 15.5, almost 16% of the patients develop sepsis. Mortality, we know that sepsis is one of the leading causes of death across the globe, and in the hematology patient population, about 47% of these patients die every year. We felt that we had a very unique opportunity to create a population-specific algorithm that would account for the unique presentation of these patients. And we want to include some lead time. And what that is the interval of time between prediction and presentation. It allows clinicians the opportunity to identify an individualized treatment plan that may decrease the progression of sepsis for that patient. In a study by Johns Hopkins, their machine learning algorithm provided clinicians with a 28.2-hour lead time. Early treatment, you know that you can predict how are you going to treat. University of California, San Francisco released a study just last year, and when treatment was initiated based on their machine learning model, they experienced decreased length of stay as well as a decrease in in-hospital mortality. So now we've identified our problem. We think we have a solution, but that solution should be supported by evidence. So how do you actually perform a literature review? I can say I've implemented a lot of different things in my career, but I've never actually gone to literature to support what I was implementing because these were projects that were determined by the organization to be, this is what we're going to do. This thing is going to generate new revenue. It's going to solve some type of business need for us. But making sure that we go back to the evidence is very important, especially with this type of project. So we know that machine learning, we hear a lot of buzz, people are talking about it a lot, but what does it really mean? And how often have people used it and how successful have they been at it? So in doing a literature review, I determined I want to know what types of studies on sepsis and machine learning have been done. And for that review, I looked at the top of this. So the evidence pyramid here tells you the best type of evidence is a meta-analysis followed by a systematic review, randomized controlled trials, and cohort studies. So I wanted to stay at the top of the pyramid. And in doing a Google search, with the key term sepsis and machine learning systematic, I got 1,250 results. I have to be honest, I did not read all of those articles. But there was one systematic review that was really good on machine learning, so I did choose to use that one. PubMed gives you access to biomedical and life science journals, and here I used the search criteria of randomized controlled trials and cohort studies. And the key terms were machine learning and sepsis. I think this one I got about 57 results, and I used 6 of these studies. The next one, sepsis prediction, was about, I think, 687. And from that one, I used 3. So knowing what you're looking for and what your date range is very important. So after you have these, now I have these 10 studies that say, yes, you must create a machine learning algorithm. But just because it's a study, how do we know how good that study is? So you have to rate the strength and the quality of the evidence. And this is an example of an evidence rating scale that is used by, it's by Johns Hopkins. It was published by Johns Hopkins, and even though we use the Iowa model for our nursing evidence-based practice model at City of Hope, I chose to use this because that particular model does not give you its own evidence appraisal tool. 9 out of 10 of the studies were non-experimental, so they had a strength level 3, and they all met the criteria for quality. They were good quality. One of the studies had an experimental design, and that one, the quality was high. So what did these have in common? There were some commonalities. One of the studies was a prospective study. So 90% of the studies used retrospective data. It was all publicly available data sets that had information from 2001 through 2016. The population were adult ICU patients over the age of 18. And they used a carry-forward computation method, which basically means every hour when the algorithm made its sepsis calculation for the prediction, if there was a vital sign that was missing, it would look for the last documented vital sign and use that for the computation. The supervised learning approach was used by all of these studies, and Nasim will talk a little bit more about what that means. But basically, all the studies predefine what characteristics or what features their algorithm would use for the sepsis prediction. Only 3 studies were interested in lead time, and the lead time was anywhere from 3 hours to 28.2. All of them compared their machine learning algorithm performance to that of an evidence-based practice model that we already use, such as MEWS, the Modified Early Warning Score, or the Surviving Sepsis Campaign criteria for SIRS. In addition to that, they also looked at SOFA criteria. They all also addressed institutional review board approval. And for those of you who are not very familiar with that, there is the Code of Regulations, Title 45, which gives you a lot of information about all the things you ever want to know about IRB approval. But if you're using data that has been de-identified, then you don't actually have to have approval. However, if you're going to publish for a research perspective, you might want to still submit so you can get a waiver of consent, meaning your participants don't actually have to sign consent to be included in the study. For us, this is a research study. We are using both identified and de-identified information. The information is, initially it was identified. We had a way to de-identify it before it was introduced into the model. After we got our first round of feedback from the model and we needed to validate, we did re-identify that information to check the validity of the model. So some of the gaps in evidence, one of the biggest ones is dependence on the ICD-9-10 codes. So what this means is if the patient has been coded as having sepsis, the patient has sepsis. But is coding always right? Sometimes, maybe not. We found this to be a bit inconsistent within our organization. So instead of relying on ICD-9-10 codes, we have determined if the patient is septic, they must have the presence of a sepsis order set and clinical documentation by a physician that the patient has sepsis. Generalizability, all of these studies were done on a general population of patients. Again, ICU patients above the age of 18. If you take those same results and apply it to a hematology and cancer population, the way that the model performs will not be the same. So we are creating a model that's going to perform well in our population of patients. From a 1-hour carry forward computation perspective, If there are multiple values that were calculated during that 1 hour time frame, the model created a mean score and used that for its risk prediction. We are doing a continuous computation. So anytime there's new data introduced into the system, automatically a new risk prediction score is going to be calculated. The censoring effect is actually pretty interesting. This is when you have a patient who receive treatment for sepsis and then they don't become septic. So you say they're not septic. So in this, you're underestimating the number of positive sepsis cases as opposed to really knowing which patients truly would have had sepsis. In our model, one of the machine learning algorithms that we use does address censoring effects. Prospective validation, there's just not a lot of studies out there that give you this information. The one from UCSF is the only one that gives you prospective information. So we have a lot of studies that say, yes, machine learning and sepsis is something great, and you can identify which patients are going to become septic. However, we don't know that to be true in real time on real life patients right now. We know that to be true of these data sets from 2001 to 2016. So we are going to be moving into our prospective validation, hopefully during third quarter of this year, and we will definitely come back and tell you what those results are. From a lead time perspective, we are looking to have a lead time of at least 4 hours for our clinicians. And treatment recommendations, again, none of the studies really provided recommendations on how to treat patients. We know that the study from University of San Francisco, they were doing early intervention, but they never really said what those interventions are. So we hope that when we finish our prospective validation phase, we will have treatment recommendations that we can share. So this list is, it's just a snapshot of features that one could include in their prediction model. It's separated into domains, so there's lots of different domains. You have transplant type, diagnosis, conditioning, labs, value signs, nursing observation, and problems. Under the features column, most of these features are based on the Surviving Sepsis campaign criteria. And we've also included features that were important for our particular population. One thing to note is when you're looking at transplant patients, there are complications associated with transplants that mimic the signs of sepsis. And that's where you see the column that says HSCT. So if your patient has a temperature, are they septic? Or are they experiencing engraftment syndrome? Are they experiencing neutropenic fever? This is where our clinicians sometimes have a little bit of difficulty determining between sepsis and some type of other complication that can happen after transplant. When we move into version 2 of our model, we plan on including additional features that will help decrease some of the noise and increase the accuracy of the predictions. So here, this is what's included in our model currently. Again, we have 676 patients. Of those patients, we know that 91 patients did have sepsis. Again, those had a physician documentation of sepsis and the presence of an order set, the sepsis order set. 585 patients did not have sepsis. And the transplant types, 245 allogenic, 431 autologous, and our median age range was 57. So the features included right now are in the domains of transplant type and disease, vital signs, lab values, as well as demographics. We're really, really excited about the work that we've done with this. And I'm going to hand it over to Nasim, who's going to speak more about what artificial intelligence is, as well as machine learning. And she'll wrap up with giving you what we found out so far, what our results have been. Thank you for your time.
Good afternoon, everyone, and thanks for being here on a Friday afternoon. I hope my accent and my struggle in doing this will help you stay awake. So before I continue with the results on our sepsis projects, I want to give a high-level overview of artificial intelligence or AI and machine learning and how we apply it to healthcare today in the industry. Artificial intelligence, in my definition, is an effort to build a system or a machine that can mimic human intelligent behavior. Machine learning is a branch of artificial intelligence where the machine is presented with a data set or big data, small data. So the machine is presented with some data, and then it tries to find patterns that help explain a problem or an outcome. Those patterns that then can be used to predict the same outcome or problem for new cases with the same data points. Deep learning is or deep neural networks, which is very popular these days. It's a new form of machine learning that is inspired by the activity of our brain neurons. And it tries to mimic the way our brain learns things through experience. When I first came to the healthcare industry from a completely tech background, I was really shocked at how things were behind in healthcare. I started working with a hospital when I first came to a startup. I worked before City of Hope, and I wanted to do a project, so I asked the data analyst on the project, how can I access the data from the bedside monitors in the hospital? And she told me very casually, oh, we don't have that data. And I said, what are you talking about? How can we not have that data? She said, oh, we might have it. It might be sitting in a server that we don't know where it is, or it might be the property of the third-party company that is providing the monitors, but we don't know where that data is. Although we have something called EMR, which the nurses go and read the vital signs from these monitors and put it into the EMR every few hours. To me, that was really shocking because I was comparing this to a company like Amazon, for example. The way Amazon uses every little bit of your information about you, and they combine it with seemingly useless data, like how many seconds you spend on this page, what is the pattern of your mouse moving on the screen, what buttons you click on, in which order, what images you look at, how many seconds, and they combine all of this data to recommend products to you or movies to you. And here we have data as valuable as the heart rate of a critically ill patient. And not only we don't do anything with it, we don't even keep it for the future use. Later on, I saw a report by McKinsey and Company, and they had ranked the industries in terms of digitalization and use of technology. And it wasn't a surprise to me anymore that healthcare was ranking 19 out of 22, and it was right after real estate and before construction. The good news, though, is that things are changing. The fact that people like me are here and we are having this discussion means that the need has been identified and acknowledged, and the industry is moving in the right direction. Many of you might remember 1956 when IBM Deep Blue beat Garry Kasparov, world chess champion. Many of the people you see in this picture who were watching the game live, they went home thinking that human intelligence will be surpassed by machine intelligence very soon, and the machines will take over, and very soon we will be extinct. Sorry. So what happened, and why are we still here? The answer is that the way a machine plays chess is very different from the way a human plays chess. When a computer is playing chess, all it does is computation of probabilities. So imagine that a machine has, for example, 20 different moves that it can make at a stage on a board game. It will do millions and millions of simulations starting with each of those moves up to the end of the game and see what happens and what's the probability of winning if it makes this move. And at the end of the day, it picks the move that has a higher probability of being in a winning scenario. But when Garry Kasparov plays chess, he does not have that level of computation power. The smartest human being can at most predict one move of chess ahead of time. But what he does have is that he can actually think. He has creativity, he has experience, he takes risks, he takes caution, and he makes the decision and makes the move. So I think we have established the fact that computers are good at math and computation, but they can't really think. How can we use this in healthcare in our advantage? If you think about a nurse or a physician that is taking care of, say, a septic patient, they have hundreds or maybe thousands of data points that they have to keep in mind anytime they want to make a decision. Like they have vital signs and lab values of this patient over time since they were admitted. They have the medication the patient is taking, their underlying disease, the patient demographic, everything about the patient. They have to keep in mind, and when they want to make a decision, they have to connect all of those dots. And it's natural for a human being to sometimes miss a few points and maybe make not a very optimal decision. But the computers can really come to rescue in these situations because they don't have limitation in terms of how many data points they can monitor in real time, and they can follow rules very well. So computers can follow thousands and thousands of interconnected rules and decision trees in the matter of milliseconds, and they have no problem with that. Okay, so I'm going to talk about AI history a little bit, and that's really important to me. So this might take a while. Please bear with me. AI has been around since 1956, and every few years it experiences amazing successes and embarrassing failures. And we as human beings, we like to build things that look like us but don't follow basic biology rules. We like to think that if computers are better than math, what if they can get better at thinking in general and create better versions of themselves and take over the world? And then we like to go and make movies about it. But the reality is actually very different. Every 50 years or so, since 1950, something comes up, like, for example, chess playing computers. And everyone gets excited, and then research money flows into AI, and a lot of great developments are made. But what happens is that usually expectations grow bigger and faster than developments. And then when these expectations are not met, the bubble around AI bursts, and we go into something that we call AI winter, where there is a few years that there is no development and no research in AI. And that's a very bad thing. So how can we prevent that? Because I think that this time AI has a really good chance of making it, because computers are stronger, and even more important than that, they are connected to each other via internet. One of the things we can do is we should be very cautious to draw the line between AI hope and AI hype, and science fiction when we think about and talk about these things. We should differentiate between general AI and stop fantasizing about it. General AI is a general purpose intelligence system that can think as well or even better than a human being. We should start appreciating narrow AI more, which is application of AI. For example, automatic translation. Nowadays, if you go on vacation, you can have an earbud in your ear that can translate from any language for you in real time. How amazing is that? Why can't we just appreciate it for what it is? And a very good practice, I always say, is that stop calling it AI and start calling it by what it does and what it does not do. Let's call it natural language processing. Let's call it machine learning. Let's call it self-driving cars instead of AI. So the problem with artificial intelligence is that it is not artificial. It's very real, and it's derived from human insights. And it's not intelligence. It's mathematics and it's computation. Now it's mathematics in its finest form. But it's not here to replace human intelligence. It's here to augment and empower us. And if you think about it, it's already done so. I can give you an example. I was sitting at my desk the other day, and a question popped in my mind, and I always have these crazy questions. I was wondering how wide is the Milky Way? And I could get my answer in a matter of 5 seconds. And those 5 seconds were because I had to type it into Google search. And even before opening any link, Google gave me the answer in a little box. And compare this to when my father when he was my age, wanted to get the answer to this question. He would have to make a trip to the library, find a book about astronomy, and start searching through the book. And in a few hours, he might or might not be able to get his answer. What we do today is hybrid thinking, and it's very different with the way people used to think before. So if you look at it, we are already empowered and augmented by machines. And I had my answer in 5 seconds, and I had all of that time that I could spare to ask more questions and learn more things or watch dog videos, which I did the second. There are some applications of machine learning in AI already. So one of the big ones is image processing and image analytics. Image processing can help pathologists and radiologists to detect very subtle changes in images that a human eye might not be able to detect. And it can help them make more accurate and faster diagnosis. Natural language processing is what helps the machines interpret free text. As you know, free text is everywhere in healthcare, from path reports, radiology reports, doctors and nurse documentation, scanned documents, PDFs, and it's very hard for the machines to digest these data in a free text format, and it needs to be in a discrete format to be digested by most algorithms. And what natural language processing does is that it interprets free text and puts it in a discrete format. Cybersecurity is very big these days in machine learning. Machines can help detect and block ransomware. They can also help with creating channels, secure channels for exchange of sensitive patient information. Last but not least is clinical decision support and predictive analytics, which is what our team is mainly focused on currently. And our sepsis project falls into this category. Going back to the sepsis project, how does the machine learn about sepsis? As I said, with machine learning, it's all about detecting patterns. So the machine looks at the data and tries to detect patterns that are different in septic patients or patients who did get sepsis and patients who did not end up with sepsis. I can show you some examples of those patterns that can be easily seen in 2 dimensions. Now, this is a subset of our data. I'm not by any means generalizing this to all of the transplant patients. These figures are only for me to be able to make a point. If you look at this, most of our sepsis cases happened between day 5 and 10 from transplant. So on the x-axis, you have days from transplant, and in the y-axis, you have number of patients who got sepsis. So when the machine sees this, it says immediately, okay, so I should keep an eye on day 5 to day 10. These days seem to be risky days for transplant patients. What you see here on top, the red line is heart rate over time from 1 week before to 3 weeks after transplant for septic and non-septic patients. The red one is for septic patients, and the green one is for non-septic patients. The 2 lines on the bottom are for same thing for creatinine levels. And you can see very obviously that before transplant, so day 0 here is the day of transplant. And before transplant, the pattern is not significantly different. But after transplant, you can see that the pattern for heart rate and creatinine levels is significantly different for septic and non-septic patients. This one is the same thing for temperature, the one on top. And if I look at it, you see 2 overlapping lines, that is for septic and non-septic patients. When I look at it as a human, I say, okay, so this shows that temperature, median or average of temperature is not that different between septic and non-septic patients. So I might think that temperature is not a very important variable in this thing. But when the machine looks at temperature, it not only looks at absolute values and median and average, it also looks at other metrics of these, what we call time series data, or the signal. It also looks at how much temperature fluctuates, or what's the variance of temperature for septic and non-septic patients. And that's the graph you see on the bottom, which you can see that when we look at variance, it's actually significantly different between the two populations. This one is weight of patients at admission. So when they were admitted, the green dots is weight for the patients who did not get sepsis, and the red ones are the dots for patients who did get sepsis. And if you look at it, patients who did get sepsis had a median or average weight that was less than the patients who did not get sepsis. Now, this might be a confounding variable. This might have to do with something else. This might be because the patients who did get sepsis, they were more ill when they came in, so their weight was less. But in terms of prediction, this turned out to be a predictive variable that could predict sepsis in these patients for us. So how did we design our machine learning algorithm? We trained 4 different algorithms, machine learning algorithms, and each of them, at each point in time, when a new data point becomes available, they create a risk score based on the patterns they have detected in historical data. When they see a new patient, each of them monitor the patients in real time, and they create a risk score when new data becomes available. And the final risk index is the sum of all those 4. And when it passes a threshold and stays higher than the threshold for 8 consecutive hours, that's when the system flags this patient as being high risk of sepsis. I don't know if this is visible enough, but the graph we have on the bottom left is for a patient who never got sepsis, and it was not flagged by our system. You can see that in some hours, and the bars are the risk index at each hour after transplant. You can see that in some hours, the patient did pass the threshold of being high risk, but because it was not for 8 consecutive hours, the patient was not flagged. And the red graph is for a patient who did get sepsis and was flagged by our system. And you can see the blue dot there is where after 8 consecutive hours, the system has flagged this patient as being high risk. And the gray dot is when the patient in real world was really diagnosed with sepsis in hospital. And for this specific patient, we had a lead time of like 24 hours, which makes you think, if the physicians knew 24 hours before this happened, what could they do about sepsis? And that opens a whole new window of research, because no one has ever been able to predict sepsis. If this thing works, and if it can predict sepsis ahead of time, then people can go research. Now that we know the patient is going to be most probably to be septic, what can we do about it? Because transplant patients, they are already on fluids, they are already on antibiotics, and we don't really know even if this lead time means anything, if they can do anything differently. So our results are presented here as area under the receiving operating curve, or ROC curve. ROC curves are what we usually use to show the performance of such predictive models. And the gray line you see here is the ROC curve for just flipping a coin. So if you have a septic patient, a transplant patient, and you flip a coin to say whether or not they're going to be septic, the gray line will be the ROC curve. So, and the higher you go above that, and the more the area under the curve is, the better your prediction is. The red rock curve you see here is for MEWS. MEWS is a detective model for sepsis and patient deterioration, which is very widely used, but it does not work very well on our population. You can see here that for a true positive rate of 73%, which means if MEWS wanted to detect 73% of septic patients, it would have false positive rate of 49%. So that's not what really we can use in real world, because 50% of the patients will be falsely flagged as being at high risk. And if you want to compare our algorithm to MEWS on this population, we have at the same true positive rate of 73%, we have only 14% false positives, which is a huge improvement over MEWS, but this is just the start of this research and just the tip of the iceberg. So this is an ongoing effort, and we are trying to make this even better. Our overall results are area under the curve of 0.9 on around 0.9 on both training and validation set. So we did have a validation set that was never used for training the model. It was kept aside only for validation. So our next steps, we actually have a next step 0, which is improving the performance of the model using more data and more features. Then we will be validating, we are now designing a live pilot to validate our results on real-time data, like Tushondra mentioned. And hopefully when the real-time validation is successful, we'll disseminate the results internally with our stakeholders and also externally through publications. And then we will have a discussion of interventional IRBs, and that's the question of, now that we know sepsis is going to happen, what can we do about it? So that will be a different area of research and will require its own IRB. And if we want to do any intervention, then there needs to be a notification process, who needs to be notified and how they need to be notified, and in which media. And then there needs to be communication and training plan for people who are going to get those notifications. Thank you very much for bearing with me, and you see our contact information here, and we'll be taking questions.